So this is the integral that we've come back and forth to a few times over the past few weeks. Now this integral is not exactly a hard one, but it is a very, very complex one. It involves four major techniques, which is why it's such a good example when we're getting to the point of kind of bringing it all together and utilizing all the integration techniques that we've learned right here. So this is a very good example for bringing several things together. This is going to involve 2u substitutions, trig substitution, and a partial fraction decomposition. So it is, while it is seemingly a very easy one to work, in actuality it's very complex, and there's several different ways we need to think about this in order to break it down. So this is an excellent integral to practice on and to really understand all of our techniques. So basically, I happen to notice right away that I'm dealing with tangent here. Now I know the integral of tangent, I know the derivative of tangent, and I know a great deal about it. The difficulty here is the fact that I have a square root sign. That's what's causing me a problem, if you will, and making this into a non-straightforward integral. If I were to try something like u substitution, tradition would tell me to make the u substitution with whatever is underneath this radical sign right here. But that's not going to do me much good in this case, because if I make u equal to tangent of x, I'm still going to have trouble with this square root sign. So basically what we're going to have to do is make a u substitution with the entire thing here and try to slowly manipulate this into something that we can work with. So let's start off by making a u substitution and say let u equal the square root of tangent of x. Now if I do that, I want to get rid of this square root sign, so that means if I square both sides, I have u squared is equal to the tangent of x. So now instead of taking my du directly from here, I'd rather do it from here, so I'm going to implicitly differentiate both sides. With respect to x. So if I do that, bringing down my 2, this becomes 2u du dx is equal to, and the derivative of tangent with respect to x is secant squared of x. So now what I want to do is solve for my dx, because that's what I need to plug back into this equation right here. So if I do that, right now I'm dividing by dx, so I will do the opposite of that, multiply both sides by dx. If I do that, I end up with 2u du equals secant squared of x dx. So now I'm multiplying secant squared times x, so I will divide both sides by secant squared of x, and I get that 2u du divided by secant squared of x is equal to dx. So now I have a dx that I can plug back into here, and I also have a u substitution, so I can rewrite this integral as u, and plugging in my dx down here, times 2u du over secant squared of x. But I still have one difficulty here. Notice that I still have an x in my denominator, and I'm now trying to get this solely in terms of u so that I can integrate with respect to one variable. So what I need to do is come up with an expression in terms of u for secant squared of x. Well, when I'm defining u in the first place, I'm defining it in terms of a tangent right here. So in order to get an expression for secant squared, let's go over here and draw a right triangle. Now what I'm saying is that the tangent is equal to u squared. Tangent, as we know, is defined as the opposite over the adjacent. So the opposite side divided by the adjacent side is equal to u squared. U squared, of course, can be expressed as u squared over 1. So that means my opposite side is u squared, and my adjacent side must be 1. My opposite over my adjacent and I can draw this as an arbitrary angle x. So the tangent of my x is my opposite over adjacent, u squared divided by 1, just u squared. So now, if my tangent of x equals u squared over 1, first I need to find my hypotenuse here because I need to convert this into terms of cosine and secant. So if I want to find my hypotenuse here, I say by Pythagorean theorem that's 1 squared plus u squared squared equals the length of my hypotenuse squared. 1 squared is of course 1, u squared squared becomes u to the 4th, and that equals c squared. This means my hypotenuse is just the square root of 1 plus u to the 4th. So this side right here has a length 1 plus u to the 4th. So now that I have all three sides of my right triangle, I can define the cosine of x is my adjacent over the hypotenuse. So in this case, that would be 1 over the square root of 1 plus u to the 4th. And if that's my cosine, then cosine squared of x would be squaring the 1 becomes a 1, and squaring a square root, those cancel, and I'm left with 1 plus u to the 4th. And if my cosine squared equals this, then my secant squared, secant is just the reciprocal of cosine, so we simply take this and turn it on its head. So my secant squared is 1 plus u to the 4th. Just simply taking this fraction and flipping it over. So now I have an expression in terms of u for secant squared of x, and I can take this and plug it back into here. Therefore, my integral becomes u times 2u over 1 plus u to the 4th du. And of course I can simplify this a little by multiplying through my u. So this becomes 2u squared over 1 plus u to the 4th du. So now I have something that I can work with a little bit better. I have something solely in terms of u now.